Hello everyone, welcome to organolysis. So welcome to another session of the name reaction series. Now in this particular video we are going to discuss about the Mitsunobu reaction. Now it's a very much important reaction for CSIR-NET and GATE as well. So this reaction is quite new and the reagents quite new for you, so that's why the reaction is very much important and question frequently asked from this topic. As you can see previous year questions, they frequently asked question from this topic. So I also do some previous year question and at the end of this video, right? So let's start the video. First of all, you have to know the reagents and the substrate and what will be the product. Now first of all, the reagent the substrate is basically the 1 degree or 2 degree alcohol. Now when we are using this alcohol, you can see here it is a chiral center, and if you have this OH group is in the above the plane, the main motive for this reaction is to change the stereochemistry of this particular alcohol. So that is why this reaction is very much important. And you can say when you have seen the overall mechanism or the reagents, then you can easily predict that it's a modified version of SN2 reaction, where you can already see that the inversion of configuration has been takes place. So that is why this reaction is important. You have to change the stereochemistry of this particular alcohol. So see first that you have a nucleophilic hydrogen and you have this kind of group and the PY3. This now see this Y may be different kind of group, like if you have any pH or any alkyl group, so that's why Y may be different for. So I am just written over here a generalized sequence of this reaction, and you are getting, as you can see here, this OH is in above the plane. So you can see here this is our product. From here you can see that the substitution with the inversion has been takes place. This is an incoming nucleophile which is in below the plane, and this is the overall reduced group, and this is the side product. Now see the mechanism first. Now when the Mitsunobu in the year of 1967, so the reaction was found in 1967. So the Mitsunobu first reported this kind of reaction. Then he first choose the reagent that is called DEAD. So this is called DEAD. So this is a quite new and quite important reagent. This is basically called the DEAD. Now what is DEAD? DEAD is basically diethyl azo dicarboxylate. So this is called diethyl azo dicarboxylate and it is called DEAD. Now when we are using this DEAD in the PY3, as you can see here, the Y here is the pH. So this is your PPH3 group. Now how the reaction takes place first. So now this first step for this reaction is the PPH3 has a lone pair, so it will attack this nitrogen center and these bonds go with this nitrogen, right? So you have the negative charge over here and you have the PPH3 plus and this overall group. Now this is basically the zwitterionic adduct. Now what is the step 2? Now the step 2 is basically this negative charge takes a proton from this nucleophilic hydrogen and this goes like this. So you can see here this Nu minus is free and you are getting this kind of product. Now the important step is this, the substrate. As you can see here, we have taken this 2 degree alcohol if the R1 or R2 any alkyl group. If the any of the R1 is a hydrogen, so this will be called 1 degree alcohol. Now this oxygen has a lone pair. Now you know that very well the oxygen and phosphorus has a high tendency to form bond. That is just because the strong bond formation has been takes place. So that is why it will attack over the phosphorus center and these bonds go like this. Now you are getting this kind of intermediate. This oxygen now is become plus and you have the nitrogen is minus. So this nitrogen takes a proton from here and you will get the product. The side product is basically looks like this. This is your hydrogen, this is your hydrogen, CO280, and this is your CO280. As you can see here, this is your side product. Now you can see here this is now a very good leaving group just because it has a tendency to form the phosphorus oxygen double bond. So if the nucleophilic attack is in the back side, so it will form bond this like this, and you are getting this final product that you have, that is the inversion of configuration, and the side product is the PPH3 double bond, which is very much favorable. So that is why this overall reaction takes place. Now I am taking here, when we are taking the dead, as you can see here I have written this R3 and R3, and when we are using CO2 in the place of R, it will be called dead. Now when we are using CO2 IPR, that is a CO isopropyl group, when we are using in the place of R3, it will be called DIAD, that is basically diisopropyl azo-dicarboxylate. So this is nothing much different. So it is also used for this Mitsunobu reaction. Now another thing is, then what will be the nucleophilic center? The nucleophilic center may be the oxygen bounded with this, and or maybe the sulfur, or maybe the nitrogen, or maybe the carbon kind of nucleophile. Now I am written over here a short note for you, that you can easily understood that how this reaction takes place for a different kind of nucleophiles. Now when we are using this is our main substrate that we are using is this one, that is OH is in the above the plane. So our prime motive is to change the stereochemistry of this particular OH. So when we are using this dead in the presence of PPH3, and this is our nucleophilic center. So when we are using this, now you can see here the OH, the stereochemistry of OH has to change in the below the plane, and the nucleophile should attack in the below the plane. So that is why you are getting this OCOR. You can write here, that is in this way. So this O minus, and it can attack over here, and you are getting this final product. And now subsequently the hydrolysis of basic hydrolysis, you are getting this product. So basic hydrolysis is basically in this way and this way. You are getting this final product after the hydrolysis. Now you can see here when we are using DIAD, so I already said here that is the CO2 IPR group when we are using. So if we are using DIAD in PPH3, and when we are using R5 and XH, so X may be here the X may be your oxygen, or X may be your sulfide. When the X is your any oxygen, so it will be called the ether cleavage, or ether kind of product. And when you are using this S, that is sulfur, in this X position, that will be called sulfide. So you are getting this kind of intermediate, that this is your nucleophilic hydrogen, this is your hydrogen, this will abstracted by this overall group, and this X minus will directly attack over here. That will be you are getting this product. Now when we are using the same concept, that is DEAD in the R2NH, and this is your HN3 and DPPA. Now what about the structure of DPPA? Now this is very important reagent for SMID reaction, or this kind of reagent, this kind of reaction. So DPPA is basically called diphenyl phosphoryl diazide. You can see diphenyl phosphoryl azide. So this is called DPPA. So this is basically a source of azide group. Now what is the structure of it? Now you can see here, this is the structure of DPPA, right? So this is the structure, and this is the nucleophilic center that will attack to this primary secondary alcohol. Now when we are using this condition, when we are first of all when we are using this one, that is R2NH, so you can see here this nitrogen, if this hydrogen is abstracted by this group, and the nitrogen nucleophile directly attack over here, you are getting this product. Now when we are using this condition, or HN3, so this is basically the source of azide group. So this azide will attack over here, and you are getting this alkyl azide. And when you have the NR2, that is called alkyl amine. Now similar condition when we have the dead and PPH3, there is a 2R group, that is 2Z group. So Z may be different kind of alkyl or aryl group, that is abstracted, that is electron withdrawing group, just because you can see here you have to produce a negative charge over here that will attack to this alcohol. So the Z may be your CO2 any alkyl, or this kind of group that can stabilize this negative charge, right? So that is what it is. Then you are getting this for product. Now some key points that you should remember for this overall Mitsunobu reaction is that I already said that this is a modified version of SN2 reaction. That is, the inversion of configuration is our prime motive for this reaction. Now the second thing is that 1 degree or 2 degree alcohol is a base substrate for it. Now that when we are using 3 degree alcohol, that doesn't undergo this Mitsunobu reaction. So this is our third point. Now the next important thing is that the reagent. So this, if you see here any question or any kind of reagent, when you have given this date or PPSA, you can easily predict the reaction should be Mitsunobu reaction. So this is very much popular reagent for this reaction, and the date is basically used for this reagent as a prime reagent for the Mitsunobu reaction. Now let's see some examples for this reaction, and then subsequently we'll move on to the previous year's questions also. Now let's have a look this first substrate that you have given when you are using PPH3 dead, and you can see here PHCO3H. So this hydrogen will abstracted by this overall reaction of the overall group, and this PHC double bond O minus, this O minus will directly attack over here, and it will change the stereochemistry of this OH. As you can see here, the product of it is the COO minus, right? So this is our overall product for this reaction. Now see the next example for this reaction. This is, you have given the substrate like this. You have given the OH is in the below the plane, so you have to make it is in the above the plane. So see that when you are using the same group, same kind of reagent, and this is our nucleophile. So this ArSO3 minus, so this will attack to this center and to remove this overall group with this PH3P double bond O. This facilitates the reaction just because you have to convert this OH as the OH in a very good leaving group. So this is a very much good leaving group, so that is why this overall reaction takes place. So this is the driving force for this reaction. Now let's see another example for this reaction is that you have given this substrate. As you can see here, this OH is in above the plane, and you have given this condition DPPA. Now you can see here that DPPA is now your nucleophile. So nucleophile DPPA is a source of azide. So N3 minus will attack to this center that you have given this N3, right? If you have this group in the PPH3, then what will be the product? You can easily say that this is the Studinger reduction. When we are using PPH3 in your azide, your final product, I am not writing the overall structure. So this is your final product. That is a conversion of N3 to NH2. So this is called Studinger reduction, right? So this is your Studinger reaction. So if you don't know what is the Studinger reaction, how takes place, and how the reagent produce this N3 to NH2, you can go over here. I already made a separate video of Studinger reduction. You can go and check out that video. Now let's see the previous year questions, which is important. That is, you can see here that is just in the year CSIR-NET in June 2012. They have given this substrate and the same reagent, that is PPH3 dead, and you can see here this 2-iodophenol. So that is your now nucleophile. Now when we are using this substrate, you can easily predict that what will be the product. Now product is basically looks like this. This is your group. This can go here. Now you know that the stereochemistry of OH has to change. So if you have this OH is above the plane, then this OH should be in below the plane. Now what about the 2-iodophenol? Now the 2-iodophenol is look like this. This is iodo. This is your OH. Now this is your 2-iodophenol. Now this 2-iodophenol, this oxygen, this hydrogen this hydrogen is abstracted by this overall reaction of this PPH3 and dead. Then you are getting this O minus, and the final product it looks like. So this O minus directly attack over here, and you are getting the final product. So that is what you get. This is the final product. So this is your A. Now what about a B? You have given this BU3SNH and AIBN. So you know that this is a source of radical. So this BU3, this is a radical initiator. AIBN is a radical initiator, and the BU3SNH is basically BU3SN this hydrogen, this is a source of it will break in this two radical, and it is source of this overall group. Now you have to predict what will be the product of B. Now the product of B is basically it will breaks, this double bond will break in this way, and there is a bond breaking between in this way. So you are getting these two radical over here, and after that these two radical will recombine to each other, and the final product that you get is this cyclic product via a 5-membered ring. So this is your product, this is your O. Now here this is your pH, and this is your bond, this is your bond. Now write like this, and you can see, sorry, this is not, this is actually this bond like this, and this here you have the hydrogen which is in above the plane, and here you have the methyl which is in above the plane. So the product looks like this. So this is your product. This is now in plane. Now you can write it, this hydrogen is here and this methyl is like this. So this is your final product, and this question came for 4 marks. So this is very much important question that came in CSIR-NET June 2012. Now the next question, this you can see here that how frequent this question, that is June 2012, after this June December 2013, the different question comes that you have given this substrate and you have to put this PPH3 and THF and PPH3 dead and 4-nitrobenzoic acid and subsequently K2CO3 and methanol. Now first you have to know the step, we are moving the step by step. When we are using BH3 THF and H2O2 NaOH, so what will be the product? So this is, you all know that this is your hydroboration oxidation reaction, so, and it is a syn addition. So this addition is an addition reaction, so this is your syn addition product is being takes place. So you can see here this group is in above the plane. So when the hydroboration oxidation takes place, so it should takes place in the below the plane. So that is what you get. I have not written the overall mechanism for this reaction, that you have this one, this is your above the plane, and then the hydroboration oxidation takes place in this double bond. So you can see here this is your hydrogen and this is your oxygen. So this is your product. Now the how tricky the question was, that is you don't have this OH, so you have to prepare the OH first, then you have to do this overall reaction, that is Mitsunobu reaction. So this is your Mitsunobu reagent, PPH3 dead and 4-nitrobenzoic acid. Now this 4-nitrobenzoic acid is basically your nucleophile. Now when you are using this Mitsunobu, so 4-nitrobenzoic acid is basically like this, double bond O, and this is your OH. Now this hydrogen is abstracted by this overall PPH3 and dead, and this O minus directly attack over here, and it will remove this overall PPH3 double bond O. Then the final product that you get is, and then most important thing is that the stereochemistry which has to change. So now it is in below the plane. Now the reaction of Mitsunobu, after the reaction of Mitsunobu, you will get this product, that is this one, that is OC double bond O. So this is your NO2, and the further they have given this K2CO3 methanol. So it is basically the in the hydrolysis of this group, that is the hydrolysis of this group is here, then the final product this one. So this is your final product that you get. This is your no methyl, right? So this is the overall product. So see like how important the question was, that is came in December 2013. Now the next question is this one. Now this question is very much important, that they have given some lot of reagent, and you have to know the role of every reagent, then you can predict the product. Now we are moving step by step. First they given the Luce reduction, that is NaBH4CaCl3 condition. So if you don't know the concept of Luce reduction, I already made a video on different kinds of reduction reaction. So I have made a video of reduction reaction series, you can go the description for the overall link for this reduction reaction series. You can go here, and then you can easily understand what is the mechanism of the Luche reduction. So if you know the Luche reduction, it specifically reduce this ketone group, that is this one. So it will not react with this, it will not react with the double bond or something else, right? So the product, now what the concept of the reaction is the product. Now what will be the product? Now you can see here that is the hydrogen is in the below the plane. So if the hydrogen is sorry, this is not below the plane, it is above the plane. So if the hydrogen is in the above the plane, so this overall 2 5-membered ring is look like this. So if it is look like this, now this is your hydrogen, this top position is your hydrogen, and the down you have given this to hydrogen, and this overall group is like this. So you can see here this and the attack of this lower side is very much difficult. So that is why this hydride will should attack from the above the plane, and this OH will give you in the below the plane. So you are getting this product, that is below the plane, the OH. Now after that they have given this one, that is H2IRCOD. Now a big reagent. Now what is the role of this reagent? So it is a role of, what it can do, it can do the hydrogenation. You can see here this H2 is given. So this is basically an active catalyst, that is iridium catalyst. Now this basically coordinate with this OH, and the very important thing is that if this OH is in the below the plane, then these two hydrogen will reduce the double bond in below the plane. If there is a OH is in the above the plane, then this overall group, that is basically this oxygen is coordinated with the iridium. Basically this oxygen is coordinated with the iridium complex. So when it combines with the iridium complex, then this hydrogen addition should takes place in below the plane. So if it is in above the plane, this hydrogen addition should be in above the plane, right? So you can see here this OH in below the plane. So the complex that is reduced this double bond basically. So what will be the product? This product looks like this. This is your hydrogen, this is your hydrogen, this 2-methyl like this, this is your OH. So it doesn't react with the other group, it will just reduce this double bond only. So if this hydrogenation takes place from below the plane, so this 2-methyl group should in above the plane. So this is all about this role of this reagent. Now when we are using this condition, that is PPH there, you can see here that is the basically the Mitsunobu reagent. So it has, what is the role of this reagent? To change the stereochemistry of this OH group. So when it is in above the plane, you can see here that is when it's changed the stereochemistry of the OH, and you can see here this O, C double bond O, pH, right? So I might made a mistake that the question given some more reagent, that is basically the pH CO2OH, right? So this is the reagent. So I have missed that one. So this is your overall product, and the subsequently they have given the LAH, that is lithium aluminum hydride. So what is the role of it? So the basic role for it, this is heteroatom bond cleavage, that is this one, that the carbon oxygen bond cleavage has been takes place. Then we are getting this product, that is your hydrogen, that is your hydrogen, this one and this one, and you can see here this is your overall product for this reaction, right? Now see how tricky the question is. You have to know the role of every reagent, then you can predict what will be the product, right? So I hope I covered all those topics related to this Mitsunobu reaction, and I hope this video is very much helpful for you. If you have find this video useful, keep sharing my videos in your friend circle, and if you like this video, don't forget to share and subscribe this channel and press the bell icon to get the early notification from my channel, right? So that's it for this video, and thank you so much for watching.